Okay, so last time we talked about Sylows' first theorem, that every group has a Sylow P subgroup for every prime P, and we proved that. That was Theorem 465. Today we'll talk about a second theorem that Sylow proved. He proved that anytime you have a P subgroup of a group, it's a subgroup of some Sylow P subgroup of that group. And that's Theorem 468 in the book. And it goes like this. Let G be a group and H be a P subgroup. Okay, what does a P subgroup mean? It means it's a subgroup and it happens to be a P group. That's all it means. H is a subgroup and it happens to be a P group, so it's a P subgroup. Then there exists a Sylow P subgroup, I'll call it P, of G, such that H is a subgroup of P. So let's prove this. Okay. So to prove this, let's just grab any Sylow P subgroup of G. We know there is one by 465. So by 465, there does exist a Sylow P subgroup of G. I'll call it capital P. Now I'm going to let G act on the set of its left cosets. Now I'm going to let G act on the set of left cosets of P and G by left multiplication. We know that's an action. Let G act on, I'll call it S, the set of left cosets of P and G by left multiplication. Okay? Since H is a subgroup of G and G is acting on S, and H is a subgroup of G up here, and G is acting on S, we know H acts on S in the very same way. So let's say that. Since H is a subgroup of G, then H acts on S by left multiplication. Okay? All the subgroups of G act on S. If a group acts on a set, then every subgroup of that group acts on that set in the very same way. Okay. Now let's look at the order of S. Now, the order of S, got to remember what S is up here. Remember, S is the set of left cosets of P and G. From abstract 1, we know the set of left cosets of a subgroup in a group is equal to the order of the group over the order of the subgroup. That's called Lagrange's theorem. So that would equal the order of G over the order of P by Lagrange's theorem. Okay? But now we also know that P is a Sylow P subgroup of G. Right here. P is a Sylow P subgroup of G. So its order is the pth part of G. So when we divide its order out of G, there's no more P's left. So P doesn't divide this number because P is a Sylow P subgroup of G. So let's say that. Since P is a Sylow P subgroup of G, we know P does not divide the order of G over the order of P, which happens to be the order of S. Okay, so P doesn't divide the order of S. So thus, P doesn't divide the order of S. Now H is a P group. G's not a P group, but H is, because it says right here, H is a P subgroup of G, right here. And so we have a P group acting on a set whose order is not divisible by P. You know from the homework problem, that means there's a fixed point. From a previous homework problem, several homeworks ago. So you can say, since H is a P group, there exists something in X that's fixed by every element of H. Now the things in S are cosets, as you can see here. So there exists a coset, a left coset of P and G in S, such that H is equal to the stabilizer in H of that left coset. But this is the things in H that fix this coset. That will be a subgroup of the things in G that fix this coset. And by a previous homework problem, you found this stabilizer already. It's P conjugated by G. And so we get H is a subgroup of P conjugated by G. So let's say that. Hence, H is a subgroup of P conjugated by G. And now realize why you're done. By a previous homework problem, the order of this subgroup, P conjugated by G, is the order of P, which is the pth part of G, because P was a Sylow P subgroup of G. So you could say, but the order of P conjugated by G, is equal to, by a homework problem, a previous homework problem, the order of P. And so, P conjugated by G is a Sylow P subgroup of G. And that's the end of the theorem. And you can see H is inside of it, right here. And so you can put your little box there. Yeehaw. Now someone asked a homework problem, I believe it's number 6, so let's do that. So in the current homework, number 6, someone asked. So let's do that. It went like this. Let G be a group H be a subgroup of G, and P be the smallest prime that divides the order of G. Okay? If the order of G over the order of H is that prime P, prove H is a normal subgroup of G. And for this we need an action. Okay? So let's prove it. Okay, so obviously I'm going to let G act on the left cosets of H and G because we know there's P of them right here by Lagrange. So let G act on S, which would be the set of left cosets of H and G by left multiplication. By left multiplication. And now I need to mention the map behind the action because we have to examine its kernel via the map phi from G into sim S. Okay? And let's give its kernel a name. And let's let K be its kernel. Okay? You know that from abstract 1, the kernel of a homomorphism, any homomorphism, is a normal subgroup every time. Okay? So let's say that and remember that. Then K is a normal subgroup of G. And let's talk about the order of S. And the order of S would equal the order of G over the order of H by Lagrange from abstract 1. Okay? Also, you've computed this kernel. You've computed this kernel in a previous homework problem, many homeworks ago, back before spring break, back before COVID-19. So I'll say also, by a homework problem, K is equal to the intersection of the conjugates of H and G. But H is one of these conjugates where the little g happens to be the identity. So this is living inside H. Okay. Okay. Now I'm going to use the first isomorphism theorem. Since we have a homomorphism between these two groups here, I'm circling it here, I can use the first isomorphism theorem by the first isomorphism theorem G mod the kernel of the homomorphism, which we've called K, is isomorphic to the image of G. Now the image of G lives in the group sim S. So that's a subgroup of sim S. Because the image of a group under a homomorphism is a group. So this is a subgroup of sim S. Okay? Now I'm going to crash through with order bars. So you could say, thus, the order of G over the order of K, which equals the order of this quotient group, G mod K, would equal the order of this image, because they're isomorphic, so they have the same order. But this image is a subgroup of this group, and the order of a subgroup always divides the order of the group it's in. So that would divide the order of Sim S. But the order of Sim S, that's the set of permutations, the group of permutations of the set S. The set S right here has order this number. So this has order, the order of G over the order of H factorial. Just like the order of Sn has n factorial. The order of Sim S has this number factorial. But by the hypotheses to the problem, this number's P. So going back down here, this is equal to P factorial. And so we get a very fascinating thing, is that this number divides P factorial. So I'm going to say that. Hence, the order of G over the order of K divides P factorial. And now use the hint that we gave you. You could say, but then the order of G over the order of H times the order of H over the order of K. Notice that this is just the order of G over the order of K, because these wipe out. The order of H is wipe out. So this number I'm writing is nothing more than this number. And so that divides P factorial. But by the hypotheses, let's go back up and show you. One of these numbers is P. And it's this number right here. So you could say, but then P times the order of H over the order of K divides P factorial. Or, now divide both sides by P. The order of H over the order of K would divide P minus 1 factorial, as one of the P's cancel. Okay? I claim this can't happen. This is very hard for this to happen right now. This thing right here is really hard to actually happen. To see why, let's take a prime that divides this number, the order of H over the order of K. I'll call it Q. Let Q be a prime such that Q divides the order of H over the order of K. Then Q would divide P minus 1 factorial. because the order of H over the order of K does, as we just said 1 second ago. Okay? That means it's less than P, because P won't divide P minus 1 factorial, or anything bigger than P. Any prime bigger than P. So I'll say it this way. Since Q is prime, and we get Q has to be strictly less than P. Can't even be equal, because P doesn't divide P minus 1 factorial. The only primes that divide P minus 1 factorial are primes that are less than P. So Q has to be less than P. But the order of H over the order of K times the order of K equals the order of H, because these cancel. And that divides the order of G, because H is a subgroup of G. Okay? So hence, or I can say hence, the order of H over the order of K divides the order of G. Yeah? Okay, so put the two together now. Since Q divides the order of H over the order of K, and the order of H over the order of K divides the order of G, we get Q divides the order of G. So you could say, therefore, because division is transitive, therefore, Q divides the order of G. Okay? But wait a minute, Q was less than P, and P was the smallest prime dividing the order of G. So I'll just say that. Since Q is less than P, we have a contradiction. We have a contradiction. We have a contradiction to the minimality of P. So what does this really contradict? Well, look at what we did. Look at where we started. We started right here in the big box. Yeah? Started right here in the big box. We took a prime that divided this number and got a contradiction. That means there's no prime that divides this number. It's kind of hard for a positive integer not to have a prime divided, but there is one way for it to happen, and only one way, is that if this number is 1. So we can say thus, the order of H over the order of K is 1. Now remember, the kernel is inside H. We mentioned that eons ago in this problem. And so, the order of H equals the order of K. Let's say it again. Since the kernel, K, is a subgroup of H, we get H is equal to the kernel. But that's normal in G. And that's the end of the proof. No way to do it but with an action. Okay, so with that being said, that's the end of today's lecture. Remember, the homework's due on Friday. Probably sometime in the next lecture, I'll tell you how to submit it, how I'm going to do it. But keep working on it. And if you have a question, ask it again. And in the next lecture, we'll address them. Have fun and stay safe. And remember, keep loving group theory.